as promised and as I've been advertising for a couple of weeks, I wanted to see if we couldn't go through some more interesting type of problems today. So today we're going to talk about something that gets a little bit of a leap down the road for you guys. This is not something typically we would throw into a standard programming class, but I feel like it's important to try to give you guys a peek as to what's coming. I feel that in the age of AI, I mean, I'm learning about AI just like you guys are, and how that integrates into the educational process, and we're trying things. We may not always do things the same way, but my guess is that the temptation is out there to use AI to solve the problems that you're presented in your COP 1000 or your programming classes like this one, or the C# or whatever classes that you're in, and that as a result you won't learn anything. I also know that, I don't do this personally, but I know people who will get the Sunday paper and grab a cup of coffee and go sit in their living room, open it up, and work on the crossword puzzle. That sort of problem solving just is mind-numbingly boring to me. I don't enjoy crossword puzzles. I enjoy some other kind of games and puzzles and stuff, but just not crossword puzzles. But people do them simply for the joy of doing them. And with us talking about, hey, how AI is affecting computer science education and going out and getting jobs in computer science with the skills that you're trying to collect here. If you graduate school and you only know how to ask Claude how to do your assignments for you, you're not going to be much use to a company out there that's interested in hiring software developers. And why would you want to do that anyway, is the way I've been looking at it. The kind of people that seem to last a long time in this industry are the ones that find that kind of problem fun to solve. And they don't want to use AI to do it because that takes the fun out of it. Now everybody gets busy and everybody gets stressed over time deadlines and things like that, and you know, has the temptation to take shortcuts and stuff like that. I don't dispute that. But to me, if you're going to choose this as a career, you're spending money, you're spending time, you're devoting a lot of energy to taking these classes, hopefully more than just a piece of paper or somebody like me telling you that you got an A in a class like this. What good is that going to do you 20 years from now when you're trying to get a promotion at some top level IT company, right? Okay. Maybe I'm preaching to the choir, you already believe that, and you're already one of those people who likes this kind of problem and just says, hey, give me harder problems, quit babying us, give us fun, hard stuff to work on. So while I can't do that because it's too far out of the curriculum, I can kind of inspire you and give you a peek at something that might be something typical that you would face as a software developer, and just to let you know, this isn't all. Just learning where to put the semicolons and the curly braces and learning the structure of Java, that's the key to the door to get into the room. But once you're into the room, there's a whole bunch of fun stuff that needs solved, and there are a lot of things out there that computer science is still working on. We haven't solved all these problems of complexity and algorithms yet. But for you to potentially get to that point where you're a valuable member to a software development team because you know this stuff exists, and to get to that frontier where you're potentially going to be working on some of the hard problems that we haven't quite solved yet and pushing forward the bounds of knowledge in our industry, you have to at least be familiar with this stuff and study it. So that's what I'm going to kind of try to introduce today. And like I said, I know I've been advertising this for a couple of weeks. I'm not guaranteed that it's going to go perfectly because I'm just sort of winging it with some of this stuff. But we'll see what we can get into. So let's say our story basically begins with, let's say that you're Santa Claus. And I mean, the real world problem here is obviously one that Amazon has to solve. But let's say that you've got a contract with let's call it the ELF package service that delivers your packages for you. And the ELFs have a fleet of trucks, and there's this whole stack of packages that Santa has ordered and needs delivered at Christmas time, okay? Simple problem, seemingly. So our constraints here, our problem we're going to set up are our trucks. We have one to many trucks, and each truck has a weight limit. It can only carry a certain number of pounds of packages before it's full. And, similar to airplanes, I know we had that UPS truck crash. I have not heard what the investigation, was it overloaded? Was there a mechanical thing? But, sometimes they put too much weight on those. And I've had passenger planes that I've ridden on where they say, hey, don't switch seats because we've allocated you to which side of the aisle to balance the weight of the airplane, and if you do that, it's going to change and make the airplane lean. Weight is a factor in some of this stuff. But we'll just say, for keeping the problem simple, that we've got these trucks and each one has a weight limit that we have to be aware of. Trucks can't carry more pounds than their weight limits. Then we've got a set of packages, so from 1 to n packages. And I guess one of the assumptions to the problem, it's not required for us to exercise the bounds of this problem, but it's possible that there's more packages than we can fit on our fleet of trucks. So the fleet of trucks is going to have to make multiple trips to get them all. And it may be kind of like the post office, where while the trucks are out there delivering, more packages are coming in, so that when they come back for round 2, well, now we got to solve the problem again from scratch because it's a different set of packages. But regardless, we're going to just tackle this where a set of trucks has a set of packages that may or may not fit onto those trucks. And the packages have 2 values. One is they've got a weight, and so we can't put more packages on the truck than the truck's weight limit supports. But it also has a second attribute. And this is common for a lot of these difficult problems. You have a second parameter that you have to optimize for. And we're going to call that, since it's a Santa Claus analogy, we're going to call that joy. So when Santa places the order, he knows exactly how much joy that package is going to bring to the recipient. And as all these packages are coming in, and the fleet of trucks is carrying them to their destination, Santa wants to make sure that we're maximizing the amount of joy delivered. However, we have to do that while honoring the weight limit of the trucks. So that's our basic problem. Most joy is possible, but not exceed the weight limit of the truck. Go. Okay? So that's our problem. Now, this is known as a kind of knapsack problem. And if you've never heard of a knapsack before, you'll run into this too in dealing with a lot of these problems. They were either early on worked on by an English guy who uses English terminology, or an old guy that uses outdated terminology. So knapsack, that's just a term for a backpack. So the knapsack problem is just a bag that has a capacity that you're going to put items in. Okay, and then the knapsack 0 or 1 variant, a lot of these problems, there's many variants where people play with and analyze different kinds of constraints on them. But each package either goes into the bag or it doesn't, as opposed to it can't be split across multiple bags. Okay, that's what that means. So we're really working on the 0-1 knapsack problem is what we're looking at. So back to Santa's issue. We've got multiple ways that we could try to solve this problem. Now I could just give you guys lab time and say, yeah, there's your problem. Figure out which packages are going to go to which trucks in order to get a lot of joy and not exceed the weight of the trucks. And you tell me, I'll tell you the list of packages and the list of trucks, and you tell me which packages go on which trucks go. And you can just play around with different algorithms. You're probably thinking, well, I'm going to have loops. I'm going to have if statements. I'm going to have to calculate weight. I'm going to have to total up and add up the weight as I put packages onto trucks. Probably going to have some lists or arrays or some kind of a data structure that I'm looping over to hold these trucks and the packages, and all those things are true. But when it comes down to what is your loop going to look like, and what is the loop going to do to try to divide up all these packages, or as many packages as you can, onto that set of trucks, that's where it gets interesting. How are you going to do it? What logic are you going to use? What approach? What algorithm? And then what are the complexity and time and space characteristics of your chosen algorithm? That's what we're talking about here. So the first, I guess, so one of the things that you'll hear people talk about when we go into problems like this is, what is the naive approach? What is the just, let's not get fancy with it, let's just brute force loop over all possible combinations, okay? So we can do that. So the approach to doing that, you remember when we were doing binary? We were looking at the decimal versus binary versus hex, and we played around a little bit with bits, zeros and ones. Well, imagine that we've got for each truck, we've got a string of bits that's the length of the number of packages that we've got. So if we've got 1,000 packages, we've got 1,000 bits. And we're going to set the bit if that package is on that truck. Make sense? And so we're going to try all possible combinations. What that means is an easy way to do that in your code is essentially to start with 0 and add 1 every time. And as you know, as we keep adding 1 to it, we'll be going 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, carry the 1. Now we've got a 1 and a 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then we add 2, we go to a 2 in the tens digit and a 0, and we keep doing that. Well, if we're counting in binary, we put a 1 in the first digit. If we add 1 to it, then we put a 1 in the second digit and go back to 0. Okay, so a 1 in the first digit means that package goes on that truck. A 1 on the second digit means the next package goes on that truck, and the first package doesn't. It's a yes or no question. If we put another 1, 2 1s mean that both of those packages go on that truck. And we could go through and test, keep adding 1, keep adding 1. So we're looping from 1 to the number of packages, and every time we do that, we figure out which bits are on, calculate the weight of those packages going on that truck, see if it fits, and if it's more joy than the previous time, and we go through every combination of all the packages onto that truck and figure out which combination fits the most joy onto that truck. And then we go to the next truck. Well, we have to also say, well, if I put the first 2 packages on the first truck, I have to remove those from the list. So I can't put those on the next truck. So now I've got 2 fewer, so my number of bits goes down. And so I keep iterating truck by truck by truck, package by package by package. And it's just a nested loop using these bits to decide which combination of packages go onto that to maximize the amount of joy. At the end, we add it all up, and hey, here's how many packages we shipped, here's how much total joy we achieved, go. The trucks go deliver their cargo, and then they come back, and we look at the packages that we've got now, add any new packages, and we just keep iterating that forever, potentially, right? So that's one algorithm for solving that problem. And like I said, I'm going to refer to that as sort of the brute force approach. We're just nested looping over all possible combinations of packages onto all trucks, okay? Well, there's let's talk just a moment about complexity and what that looks like. So when we talk about the different classifications of algorithms, you'll often see a chart like this, and it will indicate different classes of algorithms by how complex they are in terms of time. So n is generally always the number of elements. Now for us, I think that number of elements would be the number of packages, because we're mapping packages onto trucks. The number of trucks is fixed, we've got these packages, and the longer the list of packages grows, the more time it's going to take for our algorithm to process. Now the problem with our brute force approach is that it's in the class of algorithms that we would call exponential. Since one of the hints there was the fact that we can use a bit mask, 1 bit per package, which means the number of possible combinations given the number of packages is 2 to the n. Just again, going back to our binary math, if you want to know what values it can support, it's 2 to the number of bits, and that's how big it can get. So that's what we call an exponential algorithm, and it's bad. It's very, very slow. And what we would say is algorithms that are in that classification are intractable, because very quickly your problem can grow to a point where your computer does not have enough CPU power to ever finish. And it doesn't take very long to get to that point. As you can see on this chart, n factorial is even worse than exponential. There are problems out there that in order to solve them, the only known algorithm is an n factorial algorithm. And those are really, really bad. We can only really do toy problems for those kind of classifications. But exponential is not much better. It's pretty bad. So when you are somebody like Amazon and you have thousands or maybe even hundreds of thousands of packages per day, using an algorithm that's exponential is not reasonable. You can't make it work. Your your problem can grow quickly enough that your computers can't keep up with it. You can't do it. We always thought, as the population of the country grew and the post office has more and more letters to deliver, more and more packages they're trying to deliver, that, wow, why can't they do this right? Why can't they, deliver a postcard across the country in 2 days? What's wrong with them? Well, the more you get, the harder and harder at a growing rate these problems become. Small problems are manageable, but as they start to grow, they quickly become what we call intractable, which means that the time that it takes to solve them is not reasonable and is not something we can expect even our most powerful computers to solve. So that's why they started building Cray computers and, multiprocessor computers, and, now we're talking about quantum computers, because the hope is that even though the best known algorithm might be exponential or factorial, that if we get an even more powerful or a quantum computer, we might be able to make some of these hard problems tractable in the scale that we need to process them in real life. And when I say in real life, I'm talking about things like folding protein sequences or decoding DNA to figure out, you got 100 people, cancer patients in your hospital, look at their DNA and try to figure out, is there something causing them, is there some common aspect of all of their DNA? Well, when you start getting 100, 150, 200 patients, these exponential algorithms get massively difficult very quickly. It was many years of trying to do data processing before we were even able to sequence one person's DNA, one strand of DNA, because it's so large. So imagine when we're trying to say, well, why does this population of people keep getting sick? And you're trying to compare across many, many DNA sequences, it just becomes intractable very quickly. That's what we're talking about. What we'd really like to do is pick algorithms where we can start pulling those problems down into lower and lower classifications to make them very, very much more tractable in large size problems. You know, if we could sequence DNA, or if we could fold protein sequences in logarithmic time or constant time, I mean, we're dreaming there. That's like snapping your finger and having the genie solve the problem for you each time. But linear, maybe we can break off certain parts of this problem and solve them in linear time, quadratic time, polynomial time. But generally the cutoff there is polynomial. Has anybody heard of the discussion about the P versus NP in computer science? There's some really good books and movies out there about this that are that kind of can give you the context and explain it really easily, but it's a very interesting thing to learn about. You should Google it at least. But we have this break point between problems where the best known solution is non-polynomial, which means it's at least exponential on our graph here. And then there's the class of problems below that that we have come up with polynomial time solutions for solving those. And that right now is sort of our focus on hard versus not hard, or tractable versus intractable. Okay, that's where the cutoff is polynomial to exponential. Okay, so there are a lot of problems still out there that the best solution we've got for them are exponential. And if somebody could come up with a way to solve those in polynomial time, even if it's really, really slow, as long as it only grows more complex in polynomial time, it's tractable. We can solve those kind of problems. It's when it jumps over to the exponential category that we lose it. Okay? So that's what we're talking about here. See if I can get back on track a little bit. Yeah, so why the brute force problem is slow, the one that we talked about, it produces the right answer, but if we only have 30 packages, then you're talking over 1 billion combinations that we have to solve. Again, maybe your computer can handle that, but 35, well, now it's 2 to the 35th power. 40, now it's 2 to the 40th power. And we very, very quickly are getting to a point where you might start waiting seconds for your computer to finish. You might start waiting minutes, hours, and very quickly you get to a point where you've got enough packages that your computer could sit there until the sun explodes and it's still never going to finish. Okay, that's why the brute force is slow. It's simply because the way that it works, we put it in the classification of exponential in the number of packages, and boom, we're done. Okay, so let me show you a little bit about what this looks like. Haven't talked about the code much. All I did here was I created a simple main function like we've been creating in class. And again, feel free to move closer if you can't see that. I'm limited by the different classroom that we're in today, so there's not much I can do to help. But, you know, I've got my simple welcome message. I have a couple of lists. Now, what I did was I created a couple of JSON files, one that's full of trucks and one that's full of packages. And these are, you know, nothing, you know, I just have, you know, this file has 2 trucks in it, truck A and truck B. Truck A can hold 100 pounds, truck B can hold 150 pounds. This was my happy path test case. Then I've got another file called packages.json, and it has 3 packages in it with a weight value and a joy value in them. So to start off, my main function is just simply going to read those JSON files into lists. So now I have lists that I can process. I can loop over those trucks. And then I just print the two lists. Yeah, I know I'm kind of skipping over some stuff, and we haven't really dug deeply in lectures on maps and collections and this syntax of streaming, chaining operations, trucks.stream, .map.collect. There's a lot going on here, okay, and I know we haven't gone over that syntax in class yet, but that's fine. That's not what I was wanting to talk about today. So I'm just going to do some hand waving and say, exercise for the student. If you like this syntax and think it's kind of cool looking, you're curious about what it's doing, all I'm doing here is I'm printing out my list of trucks that I just read in. And then similarly, I do a similar block of code and I print out the packages that I just read in. Okay? Then I move on. Okay, now I'm going to try to solve the problem. I've got a list of packages and a list of trucks with the appropriate, they're both based on classes. Let me look at that real quick. This should be very familiar to you based on what we've done in class so far. I've got a truck class. It has a name and a weight capacity. A string and an integer. These are just data members of this class and properties that I wrapped around them to be able to get the values out if I create an instance of it. I have a constructor that takes initial values, and I have a toString. So if I want to print a truck, I don't have to write all that code. I can just, say truck, print yourself, right? So that's all a truck looks like. Similar with a package, has a name, a weight, and a joy value. Those are all implemented as properties. I have a constructor that takes those three values, and I have a toString. This should look very familiar. You guys have done this in class. So back here to the main function, I've read in my trucks and my packages. I've just, for informational purposes, I've printed them to the screen, and then I go on. So the first thing that I'm going to do is run the brute force algorithm. It's down here, solve brute force. And I'm going to pass it the list of trucks, I'm going to pass it the list of packages. Nothing too crazy here. And it's going to return me a delivery plan. Okay, we can look at the delivery plan class. What do you think it's going to have in it? Just intuitively, what would a delivery plan consist of? I pass this function the list of trucks and the list of packages. What am I going to get back? What does the ELF delivery system need to know as the solution to this problem? A route. Okay, we're not getting into mapping or what route that they have to go to deliver it, but I like where you're going with that. But what are we answering here?
I think it's the weight. And the joy.
Yeah, we're using the weights and the joy values to decide what?
If the truck can move.
Okay. More specifically, which packages go on which trucks. So we're going to have some kind of a mapping of trucks to a list of packages. That's what we're going to get back. And then, okay, informationally, while I'm doing that, I calculate the total amount of joy that this delivery plan is going to produce. Okay, that's just a byproduct. Just so I don't have to recalculate it every time I do it. But other than, doing this fancy, using a map kind of a collection, it's essentially just a list of trucks and which packages go on each truck. That's all it is. Okay, that's what we're getting back. So to sum up, I pass this function solve brute force, I pass it a list of trucks and a list of packages, and it returns a mapping of trucks and which packages go on each truck. That's all. That's all we're doing here. And then I wrapped a bunch of fancy code around it to say, what time is it? Run the algorithm, check what time it is again, subtract the two, and now I know how long it took for that to run. So again, in your own time, if you want to know how to time your own code, I've given you an example here for how to time your code. The rest of this is simply printing the results. All I'm doing is saying, hey, this is the brute force plan, print it. You know, I call the delivery plans toString function, and all it does is says, here's a list of trucks, and here's a list of packages on each truck. That's all. Nothing fancy. And it says how many seconds it took to run and what the total joy was. Okay, so first block of code here, running the brute force approach, printing the results. Then we'll get into the second option. But to finish my train of thought here, after I do the brute force approach, I'm going to do the dynamic programming implementation of the same problem, time it, and print the results. And then I'm going to do some math and, you know, compare how much more efficient the dynamic programming hopefully was than the brute force approach. Okay. And then my thank you message, and I'm done. So we've gone top to bottom, the whole main function here on the screen. That's it. Okay, so let's look at the implementation. Solve brute force. So it tries every possible combination of packages for each truck. 2 to the n exponential time complexity. Okay, so here's my outer loop for each truck. So I'm going to solve this problem for each truck. Generate all the possible combinations. So total combinations is my loop counter, or my loop limit. I'm going to loop for each truck, I'm going to loop from 0 to the total number of combinations. And that's going to count the combination of bits like I was talking about before. In binary, that will try all combinations of bits being on or off for all those packages. You know, 0 means we're not putting any packages on the truck, which is probably going to predictably produce no joy. A string of all ones means we're trying to put every package on the truck, and, you know, in realistic data sets, we're probably never going to be able to put all packages onto that one truck. But maybe we've got a truck with capacity 1 million pounds, or we've got less than 1 million pounds of packages. So yeah, maybe it is feasible in some tests that we do just throw all the packages onto one truck and we've got maximum joy and we're done. I don't know. But that's how this is working. So I'm looping for each truck, I'm going to loop from 0 through all combinations of bits on and off. Going to set a couple of counters to 0, and then I'm going to, for this particular combination, check if the bit is set. I'm going to add the weight and the joy level, and then if this combination fits in this truck and is better than any of the previous combinations that I've tried, then I'm going to save it as the combination that works for this truck. Another term that I haven't used yet, but I'll throw it out here, is called greedy, because it just grabs the best first solution and assumes that that's the one that we're going to use and moves on. And I'll come back and talk about that term greedy here in a little bit. So when I get done and I found the best combination, the best value from 0 to total combinations that produce the most weight that fits and the highest level of joy for that truck, then I put that in the plan. That's all I'm doing here. I add, hey, this truck gets this set of packages to my plan. And then at the end, And then I removed those packages. I put those packages on the truck, so now I can't put them on the next truck. They're already on this truck. So I removed those from the list of packages that I'm going to try for the next truck. And when I get done with processing every truck and every combination of packages for that truck, I've got a plan, now I return it. That's the entire solve brute force approach. Okay, just a nested loop trying every combination. Okay, the next one, now what can we do better? Okay, so let's say we've got this clever elf and he's lazy but clever. And laziness, I've always kind of felt like is a good characteristic to have as a programmer. It's this whole notion that you don't want to work any harder. You only want to work as hard as you need to and no harder to get the task done, right? That's the principle we're working on here. And so this elf, being very clever but lazy, he's trying to figure out how to do the same thing but less work, okay? So he notices, as we're going through here, that we're trying all these combinations over and over and over again, and we don't need to. And the gist of dynamic programming is trying to analyze your problem and identify subtasks that get analyzed many times. And if you've already analyzed that problem, don't try to do it in such a way that you remember that you've solved that subtask before, and before you solve it again, look in your list of solved subtasks and see if it's in there, and if it is, just use the result that you've already got. That's what we call dynamic programming. It's simply trying to, and it's not always easy. You look at a problem like this, and if I gave you guys 20 minutes to sit there and ponder this package mapping problem, it might be kind of challenging to identify what is the subtask. I won't say that the subtask can always be identified by doing it some other way. Sometimes you have to stop and attack the problem from a way where a subtask becomes evident, okay? Just because you're doing it and you can do it brute force doesn't mean that you can just go in there and say, where's the subtask? Oh yeah, pull that out and turn it into a dynamic program. Sometimes you have to stop and step back and restructure how you're solving it so that these subproblems emerge, okay? So what we're going to do here is we're still going to process each truck independently, but instead of creating this map, instead of creating this bit mask and trying all possible combinations of it, what we're going to do is we're going to create a two-dimensional table. And in that table, we're going to say, what if this package went on that truck? One of the things that, if you're following along what I just said closely, that you might quickly realize is the memory that I used on the first implementation was simply an integer. That integer that had all those bits, one bit for each package, that's not very much memory. That's one bit per package. But this, I have an integer for every element in the table, and the number of elements is going to be the number of trucks times the number of packages. So it's a lot more memory that I'm using here. That's also not uncommon when you're analyzing these problems. In order to gain processing efficiencies, you have to spend more memory to get it. Okay, so we'll file that away. But that's what we're going to do here. This algorithm is based on a table, packages by capacities. Okay, we're going to fill this table. So another thing that I guess is not intuitive to me, just jumping in and looking at the solution, I still have to solve it for every truck. for each truck, I still have to create this table. I have to create a new table with every truck. Imagine having a spiral notebook full of paper. And for the first truck, I open it up to the first page, and I make all the notes about the problem that I'm solving, which packages go best on which, on the truck or not on the truck. And then when I'm done with that truck and I figured out the best one, I rip that page out and throw it away, and I start with a clean page and a new array, a new table for the next truck. Okay? Okay. So there's a lot of memory, and as we know about the way Java works with its memory allocation and garbage collection, it may be working kind of hard in the background to kind of keep reclaiming this memory in the background, but it's okay. It's doing it. We're creating a new array for each truck. And we go through there, and instead of processing every combination, we simply fill this table, and we either include the package or not. And this is the key to it. We're backtracking to find out which were selected. And I'm going to try not to get off in the weeds on this too much, and there's cleverness involved in how knapsack is solved, and the particular algorithm they use they either copy the previous row's element, or they add to it and change it and then move on to the next one. You can get in the weeds on this algorithm and figure out how it's doing this, but the key is, instead of brute force trying every combination, we are reusing the answers that we solved previously while we try the combinations of packages, so we don't have to retry every combination. And that part is where the efficiency is gained. We're processing a two-dimensional table multiple times the number of trucks, instead of exponentially processing more and more combinations as the number of packages grows. So if my number of packages grows, the length of this two-dimensional table grows, but it's not growing exponentially in the number of combinations that we have to try in the brute force approach. And that's where the difference is between these two algorithms. Very dissimilar approaches, but that's where the secret sauce is. And then similarly, once I figure out which one of those combinations in that table was the best one for this truck, then I remove those packages from the list and put that truck's list of packages in the plan and continue looping with the next truck. At the end of that algorithm running, then I return that plan. Okay? So, back to my main function, I solved the brute force way, I solved the dynamic programming way, and then I print the results for the two. And enough talking, let's see it run. So I think I've got it processing, it's processing trucks 2 and packages 2 right now. Let me look at those really quick. Trucks 2 only has 3 trucks in it this time instead of 2, and packages 2 has 18 packages instead of just what we had 3 in the toy problem. Okay, so let's see what it does if it'll run. Okay, so my welcome message, I read the list of trucks in, printed them, there's my 3 trucks. I read the list of packages and printed them, there's my list of all the packages. Looks like I read everything correctly, that's great. Now, the brute force approach took 36 million nanoseconds and produced a total joy of 1,953 joy. The dynamic programming only only took 320,000 nanoseconds and produced the same level of joy. So quite a difference. 36 milliseconds as opposed to 0.3 milliseconds. So the brute force took over 100 times more time to solve the same problem. And the reason I point out the number of trucks and number of packages, increasing the number of trucks does make it run slower, but not as much as increasing the number of packages. If I just added a couple more packages to that list, it's going to jump to a much bigger difference. Let me see if I can do that real quick. In fact, I think for brevity I did that. I just put a couple of packages in here already, so I can just copy and paste them. Come down here to the bottom of my list, comma, add my new packages, and let's run it again. Yes. Okay, with just 2 more packages in the list, this now went up to 137 milliseconds, but the dynamic programming version only went up 0.2 milliseconds. So now it was 100 and something times faster before. By adding 2 packages to the list, now we're 240 times faster than the brute force approach. And as you continue to add packages, I mean, think about something on the scale of Amazon in one warehouse and how many thousands or even hundreds of thousands of packages that they might have. I just added 2 packages to this list, and it made a huge difference. So there you go. I mean, I hope that illustrates it. So dynamic program is a tool that we use. Somebody discovered this along the way for taking seemingly intractable problems like knapsack type flavor problems, and there's many of them out there. I thought it was interesting that you brought up the routing one, because there's a class of problems called traveling salesman and different variants of that. There's all kinds of variants. Traveling salesman with gas prices, traveling salesman with, any kind of constraint that you could imagine adding to it. There's flavors of the traveling salesman problem. But the gist of it is, you've got a traveling salesman, and that person has to visit a number of cities along his sales route in a day. What is the route that produces the optimal route that he should travel? Okay, and then you throw in, oh, I'm going to stop for lunch too. Oh, well, great, that throws my whole plan out of the window because I had to drive across town to go to lunch. So it's a similar kind of thing, that as the number of stops grows, the tractability of the problem grows even faster, to the point where you can't reasonably in a day figure out what that day's route should be, because we just don't have the computing power. So using techniques like dynamic programming are key to making those common everyday problems that we have to face and we have to solve as programmers tractable, whereas before they wouldn't be tractable with brute force type of approaches or naive type of approaches. Okay? So that's what we're talking about. One other little thing here that I find interesting about this is 1953, well, I guess with the previous one, is 1930 the highest amount of joy that we can get? Think about that for a minute. Is 1930 the best joy that we can get from these algorithms? you would think, well, what's the point of me doing this? What's the point of implementing it either way if I'm not going to be certain that there's not another solution out there where I can throw all these packages on the truck and not get a higher level of joy out of it? Isn't that one of the things that I was trying to solve for? That's where I'm going to go back to my using the term greedy. These algorithms produce a pretty good solution, generally, but not necessarily the best solution. Okay, when I say greedy, brute force says I'm going to try all possible combinations for that truck with the remaining set of packages. But I already stole a couple of the packages for the previous truck. What if the optimal, what if I can get more joy about taking one of those packages off of that truck and putting it on this truck and then letting a different package go on there? The biggest point I want to make here is this problem is even harder if you want to be guaranteed of producing the highest level of joy. We did not even solve that problem here, okay? It is absolutely possible with either one of these approaches, the brute force implementation I just went over and the dynamic programming implementation, it is possible that there could be a higher level of joy possible with a different combination. But the greedy approach does produce a solution, and it's pretty good. It's just not guaranteed to be optimal. So one of the things we as computer scientists always need to ask, is my boss asking for a solution, a fast solution, or the optimal solution? Because what algorithm we pick is going to be based on the answer to those questions. Where this becomes really important for you guys, when you graduate and you're out there and you're trying to compete, I mean, you're going to be trying to compete with people like me who are 60 years old with a PhD and 40 years of experience doing this kind of thing, and I can't get a job programming, okay? For reasons you can probably guess. There's going to be people in their 50s that you're competing with, people in their 40s that you're competing with, people in their 30s that you're competing with. And here you are, most of you are in your 20s, graduating college, going out and trying to get your first job. It was already difficult with the whole catch-22 of, well, I can't give you the job because you don't have any experience. Well, how am I supposed to get the experience if you don't give me the job, right? You've already got challenges in front of you. Now you're going to be competing with people that already know this stuff. So when you get into an interview, and I've had many interviews where this has occurred, they give me a problem like this. What do they want to know from you? Number one, they want you to ask clarifying questions. Okay, you outlined a problem. Santa's got to get all these packages on the trucks and deliver a bunch of joy to a bunch of people. Got it. What kind of a solution do you want? Do you want a solution? Do you want a quick solution? Or do you want an optimal solution? And it is what it is. I already explained the difference between the three. But you need to ask, what are you looking for here? Are you wanting something that works in the 40 minutes left in this interview? Because I can slap something out there, but I'm not going to tell you it's going to be the fastest, it's not going to necessarily be tractable, and it might not produce the optimal solution. But I can throw some code out there and I can get you an answer, right? So you need to ask that question to start with. What are you looking for? And then they're going to make a little note that says, very, very mature way of responding to my interview question. Ask a clarifying question. Plus, okay? Then it gets into, well, that's a question. Have you improved your skills enough through taking these courses that you can do the brute force approach? Can you write a nested loop and exercise all possible combinations of packages to trucks and produce an answer. And you have to go home and look in yourself in the mirror and ask yourself that question, am I able to do that? If not, that's a great place to start working on your skills. Not asking Grok, not asking ChatGPT, not asking Claude, we know they can produce it, but asking yourself, can I sit down with a blank piece of paper and write down that algorithm? Okay? Then, great, now I can produce a solution. Can I produce a quick solution? That's when you want to get an algorithms book and you want to start reading about dynamic programming. You want to start reading about hash tables. One of the reasons you'll get questions like this on interviews, why would I use a hash table? Or for this problem, what kind of collection is the best one to use? Before they even let you write any code on a problem like this, they might ask you, what kind of collection are you going to use? When I pointed out that the solution, the delivery plan uses a map. Okay, many of these collections underneath in their implementation, they use hash tables. You need to understand what that is and why. And the very key thing about that is, if you're looking something up in a list, if you have a list of integers, and you're trying to answer the question, is there a 5 in this list? What do you have to do? You have to start at the beginning and process every element of that list and see if it's a 5 before you can definitively answer yes or no, is there a 5 in this list? Well, that sounds to me like a brute force solution, right? But if you do nothing other than, instead of reading the data out of the file into a list, if you read it into a hash table, you can simply say, is there a 5 in this list? And the lookup is constant time. It's instantaneous. It doesn't require a loop to iterate over the entire list because it hashes the value 5 and says, is the value 5 in my table? Is that hash in my table? It instantly answers the question. And again, you can read the theory on why that's true, but what the person interviewing you is going to want to know is, do you know the difference between using hashes and not using hashes? The one is iterative and the other one is a constant lookup time, which greatly improves the performance of my algorithms. Okay, so now you know that. Now you're going to integrate those in and try to use techniques like dynamic programming to identify the subproblems and make sure that you're not resolving the same problem over and over again. This is a beautiful problem for that in its subtlety because, like I said, it's not obvious, it's not a trivial thing to notice this, that it's more efficient to process a two-dimensional table of values of yes-no answers for every truck in the list than it is to process every combination of packages from 1 to however many packages you've got. But when you understand how the algorithms work underneath and what the difference in their performance characteristics is, my hope is that at some point you get to a level where you say, oh, yeah, that has a brute force solution, but it's exponential in time characteristics, so for larger problems it's going to quickly become intractable. That's the answer to that question. So perhaps there's a dynamic programming approach to the problem where we can get that exponential solution down to polynomial time, and it becomes tractable. Although it's still difficult, it becomes tractable if you throw enough hardware at it. Okay, that's the answer to the question. And then, like I said, if you're going for someplace, heavy-duty senior position, someplace like Google or Microsoft or Amazon or someplace like that, they're probably then going to have you code the dynamic programming solution, or however much you can get done in 30, 40 minutes while you're there. And I just love this stuff. To me, it's cool envisioning a solution or a problem that we're facing. Like the one that I found enjoyable most recently was when I was working for a contracting company that was hired by Princess Cruise Lines to do the onboard navigation on their cruise ships for people carrying around those little medallions. Okay, and if you're in your stateroom with your medallion and you go to the screen and you say, how do I get to the pool? It has to calculate a route. Well, do I take the stairs? Do I have any accessibility issues where I'm in a wheelchair and I can't use the stairs? Do I have to go ramps the whole way? Can I use the elevator? You know, is it quicker to use the elevator or just go over here and use the ramp? All the different combinations of routes that you could take based on the constraint that you've got. What's the route? What do you recommend? And then what do you tell the user? Because I found that really fun to solve. There's established algorithms we could do. It was a problem of creating the map of the cruise ship. All the different paths had to be put into a graph data structure. Then I had to have the algorithm process that data structure to come up with the route. And then I had to express the route in terms that would make sense to the user. I couldn't just say, well, go to node 417 and from there go to node A6X, and then from there, no, it had to be something that I could understand. So I took the route that I determined and converted it into aft, 12 steps, and then turn to your starboard, and then approach the elevator, go up to deck 12. You know, it all had to be turned into English language. And you remember on the assignment where we had cubits and steps and inches and feet and yards and all those different units of measurements. Well, I thought it was cool that I could use steps so I could tell them the distances and the number of steps that it would take for them to get there. So these are real world problems that I personally find it fascinating to be given one of those problems and try to classify it, figure out the right algorithm for it, identify the right data structures to represent the problem, implement the algorithms, and then find a way to intelligently produce the results. To me, I just get a kick out of doing that. I wish I could do that every day. Okay? So hopefully that inspires you to think that this is a cool area also, and like the people that enjoy doing crossword puzzles at their kitchen table, then you'll want to get into and realize how cool it is and what a deep well it is once you start getting into this, and how much uncovered, unprocessed ground, and how many problems that there are out there that are still being studied and have yet to be solved. And, you know, jump in, the water's fine. You know, it's a lot of fun. So I hope you guys enjoyed that and get some use out of it, and that it challenges you to solve the problems yourself. I mean, even that's the thing that I get a kick out of is I have these intro programming students that are doing these Python programs, and they're just the simplest things. It's just a couple of print statements, and you just got to do the print statements in the right order, and they're going to ChatGPT and turning in their homework to ChatGPT. I'm like, seriously, you can't type in 5 lines of code and turn it in? You have to go to AI to give a solution for that? But I'm telling you guys that you're going to need AI. You're going to need its help. But if you have never heard of dynamic programming, how do you even know to ask Claude to give you a tractable solution to the problem if you've never even heard of tractability? Okay? So I'm just trying to open your eyes and challenge you and let you know that there is so much value and so much waiting for you if you figure out the problems yourself and get a kick out of it. That this is a really cool field, and it's brought me a lot of satisfaction and joy, and I wish I could do it till I was 90. So, any questions?